Okay, so thank you. I want to do two things, I guess, today in this talk. One is to give you a very quick overview of recommender systems, in particular, the kind of recommender system we call collaborative filtering recommender systems, which use reviews and ratings from a lot of users to try to make recommendations to other users. And then the other thing, of course, is to tell you how to have fun with recommender systems a little bit. Okay, so many of you probably already familiar with the idea of recommender systems, become more prevalent in the past few years. But basically, recommender systems are designed to do information filtering for users. There's lots and lots of information out there, information overload for most users. So people need to have tools intelligent tools that try to help them find things that they are particularly interested in. So recommender systems try to recommend books, video, TV shows, for example, books, news, songs, etc. And you can see some examples of maybe some of the more common ones that people use these days. Netflix, Amazon recommenders, of course, have been around for a long time. Music recommenders, such as Last.fm, Spotify, etc. So a lot of these systems, users provide some kind of a feedback, either explicit feedback or implicit feedback. Explicit feedback would be in the form of a rating. You give a 5 stars to a movie or a thumbs up or a thumbs down, let's say, to a song or something like that. Sometimes it could be implicit feedback. So you purchase an item on Amazon, for example, and that would be an implicit indication that you like that item or something along those lines. Maybe you just click on something. So, but more generally, let's call these ratings. So in a typical recommender system, you have two types of entities. You got users and items. We saw that in some of the earlier talks. It's pretty common kind of a structure, right? The utility of an item I for a user U is represented by some kind of a rating. And again, this could be an explicit thing the user provides or maybe something implicit that's derived. Then each user typically rates some subset of items. And then the job of the recommender system, of course, is to estimate or predict the unknown ratings in this system. So you can kind of visualize this as maybe a rating matrix where users have rated a bunch of items, let's say movies, but parts of this matrix are empty, right? Because users typically, in fact, it's a very sparse kind of a matrix because the users typically rate only a small fraction of items. So the recommender system, you can think of it kind of as a function that maps users and items, a pair, a user-item pair, to some particular rating. If the rating already exists, of course, you can use that maybe to make and this is the basis for doing an evaluation of a recommender system to kind of compare your predicted rating to what the user is actually given. Now, traditional recommender approaches fall into 3 general categories or 4 categories, if you wish. Collaborative filtering is probably the most common ones these days that we see out there. Another common type of approach is content-based filtering. And then there are rule-based or knowledge-based kinds of systems where explicit rules are designed for, based on the domain knowledge, for example, in a particular domain, to try to give recommendations. And there are hybrid approaches that combine, for example, content and collaborative data. They can combine maybe different types of methods and integrate those. And those are pretty common as well. So the one I want to focus on a little bit more is collaborative filtering. And when you talk about collaborative filtering, typically people think of 2 general approaches. One is what people tend to refer to as user-based collaborative filtering. The other one is item-based collaborative filtering. How many people are familiar with these 2 ideas? Anyone? If you? Not you. Okay. So, so there's the idea of user-based collaborative filtering really hinges on similarity among users, right? So for a given user, find all of the other users who are similar. And similar means they have a similar profile, right? They've given ratings on the co-rated movies or co-rated songs, they've given similar ratings. So you can compare these, and basically your idea is to find the people that are most similar in terms of tastes or judgments to this particular target user. So that's called user-based. Content-based, the item-based collaborative filtering, which I'll get to, the idea is to compare items, but you don't compare items based on the content of those items. You compare them based on, again, the ratings people have given them, right? So if two movies, for example, are rated very similarly by a large group of users, that those movies are considered to be similar to each other. So not getting into the detail here, but the most common approach for user-based collaborative filtering is to compare, to measure the correlation among users, right? So for a given user, you find other correlated users, so that's just Pearson R correlation up there. And then you make prediction by doing some kind of a weighted average of the top k neighbors. So that's the k nearest neighbor prediction approach. So here's a quick example of how that works. You got, let's say, in this case, let's say I have 7 users, and let's say I'm interested in giving Alice a recommendation. And in particular, I want to see how Alice might rate item 6, which is missing right now. So I've computed Pearson correlation with Alice, and you can see those on the right-hand column. And you can see, for example, that this is the best match, right? Now, in this case, I'm only using one neighbor, right, the top neighbor. Usually, you can use the top k neighbors and do some kind of an average. So I'm using k equals 1 in this case. And of course, this best match user has given a low rating. So in this case, my prediction for Alice is going to be that Alice is probably not going to like this movie, right, or this item, whatever it is. Item-based collaborative filtering, on the other hand, looks at the columns here, right? So the columns are the things that we compare rather than the rows. And there are different metrics that are sometimes used. The most common is to use some variation of cosine similarity, which a lot of you are probably familiar with. It's pretty typical in information retrieval, where you compare documents, for example, based on bag of words kind of this representation and so on. So each column in here is a vector, right? It's a bag of words, and then you measure the cosine of the angle between the two vectors. And in this case, you can see, since we are interested in item 6 in here, in this particular case, you can see at the bottom the cosine similarities to item 6. And you can see that item 6 is most similar to item 2. So now I can use Alice's own ratings to give a recommendation or make a prediction for Alice. Because Alice has rated item 2, and item 2 is very similar based on the ratings of all of the other users to item 6, I can predict that Alice would probably rate item 5 also as 2, right? So that's the basic idea. Again, you can use k greater than 1, so you can use multiple items in case Alice hasn't rated the most, let's say, similar item. You know, you can look at some additional ones. All right, so one other quick note is that when we are doing evaluation in this kind of a setting, the idea is to sort of, you have some sort of users already, right, that you build a model from. So you can split that into a training and a test set. Then you can split for particular users in the test set aside basically a portion of the ratings, and then try to predict those ratings based on your model. And once you predict them, then you can compare the predicted and the actual values. And then you can do different kind of metrics, right? You can use mean absolute error. A more common one is RMSE, root mean squared error, that you know, sort of average over the errors. Now, the RMSE, by the way, was the metric that was used in the Netflix prize. Anybody familiar with Netflix prize? Did you guys know? Really? It wasn't that long ago. Okay. So Netflix decided to basically create kind of a competition. In fact, you know, a lot of the competitions we see since then, you know, on Kaggle and things like that, are sort of inspired by that idea. But they released a portion of their data, you can see the statistics here. And then they said, okay, if anybody can beat using RMSE, our own in-house recommender system, you know, we give them $1 million. And of course, you know, eventually it took like 3 or 4 years, but somebody did actually win the $1 million. In fact, it was like a combination of several top teams that got together and created kind of an ensemble approach. But one of the techniques that really emerged out of this process that really became kind of a mainstay or a staple of the work in recommender system is matrix factorization. So I wanted to talk about that briefly because it ties into some of the other stuff. We'll talk about some of the Python packages that exist for doing this kind of stuff. So the basic idea is you factorize the rating matrix, right? you create factors, the idea of latent factor analysis. You create kind of a lower dimensional space. So these two factored matrices, one of them represents sort of the user's representation with respect to these latent factors that are discovered. And the other one, it would be the movie kind of a factor matrix where movies are represented in terms of some sort of latent factors. So F that you see over there in the columns for P and the rows for Q, those are our reduced number of features. It's kind of like singular value decomposition where you reduce the original representation to a lower dimensional representation. So these features are latent features, so they're not exactly like a specific genre or a specific characteristic of a movie or a user, but collectively they might represent certain combination of characteristics that make sense for this particular data. So you learn these factor matrices, and now we can represent users in terms of their general interests represented by these factors. Similarly, the movies with respect to these general characteristics represented by those factors. Once we have this, of course, the task of making a prediction becomes very easy, right? Because a prediction is simply just the dot product of one row and a column in these two matrices. So that gives you just one cell in this original rating matrix. That's an estimation, right? So you're estimating this rating, and you're doing that simply by doing this product. So the big part of the work is just learning these two factor matrices. Once you have that, essentially in constant time, you can generate the predictions for users as they're visiting the site or whatever. So that's the basic idea of matrix factorization. You can see, for example, in this just quick example, let's say that these are the two factor matrices. In this case, we have two factors, so two dimensions. And the movies, in this case, are represented in terms of these two dimensions. And that's the Q matrix. And the P matrix also represented in these two dimensions. And then you can get a prediction, let's say, for Alice and a particular movie, Eat, Pray, Love, in this case, by just doing this dot products. By the way, another way to do this kind of factorization is just to do standard singular value decomposition, right, which probably most people are familiar with. Lots of packages exist for doing that kind of stuff where you essentially do, factorize this matrix M into U, sigma, and V, and where sigma is sort of your singular values, symmetric matrix of singular values in the middle. But the U and V are then what's used as the basis for generating the predictions. All right, so nice thing about this is that you can actually then, once you have the factor matrices, you can do a lot of things, right? You can in fact think about movies and users kind of in the same space, right? And it's a lower dimensional space, so things can be done more efficiently. I can compare users to users this way. I can compare users to movies. I can compare movies to movies, and so on, right? In a hypothetical two-dimensional case, of course, normally in a realistic situation, you have a lot more dimensions, right? Typically, you do maybe 40, 50 dimensions or factors. And how do you learn these factors? The typical approach for doing that is to create an objective function. Usually, it's just the least squares kind of minimization, error minimization. And then you add other terms to it. So it's once you have this framework and you're trying to do the optimization, you can easily add things like user biases. You can add regularization terms like you normally do in regression analysis, and so on. So you add all of those. Then you do some form of gradient descent optimization or maybe some other kind of an optimization technique. So a stochastic gradient descent is a pretty common approach to use that. Basically what that means is you take your objective function here and whatever term is added to it, you find partial derivatives. Those partial derivatives are these equations that basically get updated incrementally by looking at samples from the data one at a time. And then you do these iterations until you're satisfied with your error, right? So you keep reducing the error incrementally until you get to the two-factor matrices. Okay. So fortunately for us, of course, people in this group, is that popularity of recommender systems, has led a lot of people to start developing pretty good tools, and they're getting better over time on doing the kinds of things that we were just talking about in Python, right? One of the earlier projects actually was CRAB, a recommendation framework in Python. You can see the link there. Started in pure Python, then they tried to integrate it into Scikit Toolkit, kind of like scikit-learn. I know you guys had a talk earlier this morning about scikit-learn and so on. So, and it provides options for doing standards, collaborative filtering, matrix factorization, and evaluations such as RMSE and so on. So it gives you a lot of those tools. It's not the most efficient because it didn't have, the last time I checked, it didn't have great support for sparse matrices, which you want, especially if you're dealing with huge amounts of data. Python-recsys, which actually is kind of an evolution of CRAB, does provide a lot of good support for sparse matrices and sparse arrays and so on. Another good one, another interesting one that you might want to look at is NIMFA. It's a Python library for non-negative matrix factorization. Non-negative matrix factorization, without getting into details, is basically a specific case of what we were just describing, creating these two matrices, but you start from the original matrix has to be, the values in there have to be non-negative. And so that's true in a lot of domains, including typically ratings. Although, you could imagine a situation where ratings might be negative, but in a lot of domains, basically those values are positive always. So the non-negative matrix factorization, by the way, is not just used for recommendation. It has lots of application from image processing to information retrieval, for example, and lots of other approaches. But in particular, it's useful for doing recommendations. There are some examples of that if you go to their sites. Another example is PyRSVD. This one actually implements specifically a version of the SVD-based solver for collaborative filtering. So it doesn't have really all of the other kinds of recommendation models we talked about, but it does specifically focus on SVD part. And it's pretty efficient. It's chunks of it are written in Python, so it's a little bit more efficient than some of the pure Python-based libraries. Just want to give you a couple of examples towards the end in here. Here is an example from CRAB. It comes with some sample toy data sets, so you can see the data in here, and you can then generate this nifty heat map for the ratings data. Of course, that's not very useful, of course, if you have millions of ratings and millions of users, but it's kind of neat to look at. User-based collaborative filtering. This is the example of using user-to-user similarities using Pearson correlation, so you can see quickly how you could easily do that by importing Pearson correlation, then generating a model based on Pearson correlation, and then essentially using the k-nearest neighbor. And you can see one example of using recommender for, let's say, user number 5, and this generates some set of movies and their predicted ratings for that particular user. Here's using matrix factorization implementation on CRAB. So in this one, I guess you can see you're importing this time matrix factor-based recommender, and essentially the model is built over here. You're passing it the data, the model, the word model in here corresponds to basically your matrix of ratings. And some item selection strategy, basically that's just the strategy for knowing what set of items among the recommendations you should give back to the user. And then the number of features, right? So those are the dimensions we were talking about earlier, the number of factors you want in the factorization. And then once you have that, you can then do things like, recommend to a particular user and get that. A quick example of python-recsys. In this case, you get movie lens data sets. Well, movie lens data set is one of the standard data sets typically we use in recommender systems to do evaluation. And here is where the SVD, this is SVD-based decomposition, so you can see the model being called there. Once you have done that, you have done the modeling, then you can do some very interesting things, right? You can do, for example, you can get similarities between two movies, just based on this lower dimensional space that we were talking about. So that's an example of that. You can get movies similar to a particular movie. So here's the movie similar to the Toy Story, for example. And again, this is based on similarities measured across this lower dimensional space. And here's an example of predicting a rating for a particular user and a particular item. So that's the function I was talking about that maps user item pairs to a given rating, right? And finally, here's a recommendation, I guess not finally, but one last one. Here's a recommendation of so the same thing for a user, but this time you select basically all of the non-rated items for a particular user and then generate predictions for all of those, and then you can rank them based on those predictions. And then you can use this to decide how many of those you want to actually give to a particular user. And finally, here's a example of which users like a particular movie. So you can actually find all of the users in that lower dimensional space that have similarity with this particular movie, its representation, and then rank those based on the particular predicted score. So I didn't talk about these other two. You can take a look at that. Of course, there are other interesting Python packages these days that are available that you can do these things in. There's also built-in support for doing certain kinds of factorization in scikit-learn, for example, in SciPy, in NumPy, that you can use and then build around those things sort of your own version of these recommender systems. Okay, thank you. Question? Yeah.
Which of these work best with majorly text-based data?
Text-based data? Depends what you mean by text-based data.
That you're trying to correlate or
so if you're using, so if you want to use kind of a, if you have a text-based data and you want to use its representation as sort of bag of words, like vectors, then, you know, I would say this Nympha library has a lot of good support for that. And if you do that, you know, along with scikit-learn, which has a lot of support for actually doing the pre-processing part of that, so doing vectorization and TF-IDF, you know, various other kinds of things that you need to do. Any other questions? All right, well, if you have questions later, then I'd be happy to talk to you later on. Thank you.
Thank you.